Here we go. Welcome everyone. Welcome everyone who's online. I don't know, like if you have anyone online. Guys, welcome to Apache Iceberg Meetup. I'm very pleased to see so many people attending a data conference. Quite unusual. It's usually like AI conference or meetup where we have so many people, but I don't know if you've been confused. We do have AI, Apache Iceberg. Who knows? Who knows? But yes, so we're going to talk about data and how you can use the data for AI, agentic, for analytics, and all that different stuff. First of all, I want to just start with some appreciation words to sponsors of today's meetup. Cantox, who gave us that venue, and ClickHouse, who is supporting us with some catering, so we're not starving here. Thank you very much, guys. And I want to start with introducing the community. It's quite young community, Apache Iceberg community Europe, and how it came actually to be existing. Well, me and my co-founder of a company Bacamo, well, you can call us the lazy people, because in order to get any information about Iceberg, you should fly over to San Francisco to get anything like, okay, what's Iceberg, what's happening on Iceberg, how to use Iceberg. And then we said like, oh, we should actually start something in Europe, because that will give everyone in Europe to build the community. And as you can see, we covered a couple of countries, all marked green here on a map. Still some countries to go. So for you guys, if you want to run a meetup, let me know. If you want to find a country where you would love to be as a presenter, let me know as well. So we happy to support you. And you can see like already we have a lot of different supporters. And the funny part, I don't know like if you experienced ever in one room sitting Microsoft next to Amazon or Databricks next to Snowflake. And that's what Iceberg is actually doing, exactly to allow those people to sit together in that community and not having a bloodbath, right? So that's a cool technology what we have here. By the way, who is let's put that question on Iceberg knowledge from 0 to 10. Like 0 is I can write Iceberg, and 10 I can challenge Ryan Blue. So on level 5, can you raise your hand? 1, 2, 3. Okay, cool. So then I can tell a lot of stuff today. Good. Not working. Yeah, working. All right. So as I said, Cantox, thank you. ClickHouse, thank you very much. And my name is Victor from company Vacamo, and we built Lakekeeper. So Lakekeeper is actually the brand that drives the community. We do have 5 presentations today. And you know, like in a concert, how we built that. So at the beginning is someone not really important to keep you entertained, and then the most important people, the artists, will be at the end. So stay till the end, get the whole information. So about Apache Iceberg. Well, as I said, not important or boring, and that's exactly what my topic is. It's about governance, access, security. So I'm not going to talk about how you can run a billion of rows in milliseconds. It's probably on a ClickHouse more. That's going to be a talk about and how to do some very cool stuff. I will talk about the trust infrastructure. Yeah, so in case you have like any questions later, here's my LinkedIn, my email. Just reach out to me if you want to talk about Iceberg, you want to talk about Lake, agentic, structure, unstructured data. So all the topics are welcomed. And yes, so I'm a co-founder of a company named Macamo, and we built Lakekeeper. And I will tell you in a second what Lakekeeper is, what Lakekeeper does, and so on. But before jumping into details, a very short introduction about the journey of data. And probably some of you, I don't know, 1990, Oracle, yay! We have fun. So we're in the same boat. Teradata, data warehouse, a monolithical system that actually gave you an easy way to a large amount of data you have your reporting to, and so on. Well, what happened around 2000 is internet happened, and we've got all the different data, unstructured, semi-structured, click, streams and whatever is happening. And the idea was, well, we had that monolith. Let's put just a bunch of them next to each other and call it a massive parallel processing and see what will happen. And that's how actually Hadoop and Greenplum and all the different systems came to replace to allow us to run the analytics. Well, 2010 cloud happened, and they said like we can do that better, and they actually did. They created a single button, fully managed data house, like Snowflake, Redshift, probably the most famous one. But additional to simplicity of operation of that data warehouse, what they did, they could separate compute and storage. Now, in the first time of systems of data, you can store as much as you want, petabytes of data, and provision a very small data warehouse because you run select one or other. So that was quite cool. Well, guys on the big data said we can do similar, and then Databricks is probably the main driver here, Reno as well, and Amazon as well with Athena. So it's fully managed cluster for you, but the cool part is that data is now separated as well. We see that we're trying to kind of decouple the whole stuff. So now data is stored as a key on your S3, on your Google blob, on your Azure blob, and then you can run your analytics. Well, here's the problem. Here's a system that allows you to run asset client transaction. Here's a system that allows you to run a huge amount of analytics, but without asset transaction, schema evolution, time travel, anything of that. Here's very costly system, here's less costly system, and then the community said, we kind of can improve this. And it's how we came to a lakehouse architecture with Iceberg. We have different open table formats, Delta, UDI, but Iceberg is probably the one who won or the one who will stay here. And as you can see, Iceberg made again a decomposition. So now we don't have just data, we have 2 layers, meta and data. And meta is exactly the magic that helps you to use a key file and have asset transaction and play around with it. So Iceberg. What is Iceberg? We have experts here. No? No ideas? Oh, Iceberg is just bunch of specifications. Table, view, muffin, and REST catalog. And good luck from the community to implement that specification. So we said like, okay, we want to try our luck, and we implemented the REST catalog specification with Lakekeeper. Lakekeeper is open source project. It's written in Rust. You're Rust fans? Yeah. So it's a single binary, no GVM, no garbage collection. It's super easy to start Lakekeeper, and you can use Lakekeeper with all the different compute engines, with all the different storages. And so the question is, what Iceberg actually did solve? And it's less technical question. It's more like a business question. Any ideas? What I show you a hint. That's one thing. No people on that. It unites systems, vendors. So exactly. So what we have, Iceberg is an open table format, which means it does not belong to any technology. So if you store your table or your data as an Iceberg table, you can use all different technologies to read and write. And that's exactly the situation what we have here. So I can have SAP, Snowflake, Databricks, Microsoft Fabric that can go and write to Iceberg and read from Iceberg. So which means you are not locked into a specific technology if you wanna build your analytics. And the good thing, if you store your data as Iceberg, and today you will use Snowflake, and tomorrow a student will drop by and say, "Oh, I know DuckDB." No problem, just use your DuckDB with my Iceberg, and you're good to go. I don't need to migrate my data. I don't need to do anything. I'm very comfortable from the situation of my data. Well, if you have a question, what it solved, it's interoperability. So we can use that interoperable with all the different systems. The second question is what it did not solve. Any ideas? You know what will happen in that situation, and especially when I talk to all the different companies, and especially bigger companies, they have all of them. Databricks, Snowflake in one company. And any of them is just asking for one thing, because now I have a way to read and write. But the question is, who is reading my data? Who is writing my data? Is not really answered. So the governance part is quite open. And the question is like, okay, so I have a Peter and Anna, and now it's like, can Peter read? Can Anna write? We don't know how to solve it. So what vendors started to build catalogs. You have on every vendor a catalog that actually tries to solve the idea of governance. Unfortunately, they solve it in an old-fashioned way, as they solved before the data, in a proprietary local way. So it's more working with their own platform, and it's not that open. So if you use Unity, it's kind of like, yes, you can read, but you will actually decide how, and you need to apply to follow the rules of Unity and so on. Same on Horizon and OneLake and so on. So the idea, what we actually trying to solve here is, well, why not to make governance independent from a compute, as data became independent. So why not governance is a layer, open governance layer that allows you actually to store your governance somewhere, and you can just go and apply whatever compute engine you have in place. It might be ClickHouse, it might be DuckDB, it might be Trino, whatever you want, but you are not tied to that governance of that specific environment. How Lakekeeper solves that? So here is a diagram. So Lakekeeper, you can run that, in our case, on Kubernetes, for instance, and then you have your data in object storage. The decision what we made, that Lakekeeper is not the IDP. So you have your central identity provider, it's Okta, your Entra ID, I don't know, whatever you use inside of your um, organization, then you can use it. Because the identity should lives in that one single place and not somewhere else, where you can create your personal access token, give it to someone, and hope that nothing bad will happen, right? So then you have like a central place to manage identities. With Iceberg, we have two different type of computes. We have a general compute that can be like a Spark or batch job that will write data, and that usually uses the client identity and secret, that specific service principle, where you don't have like many, you have just a single one. And then we have a second type of compute, which we call a trusted compute. And for instance, it's Reno, where you have a multi-user system where you need to understand, like Alice and Bob, different departments, different roles. So how can I manage that? Because the connection from Trino to Lakekeeper or any REST catalog will be done with a technical user, which means you have a technical user which has a dot mode and can read everything, and you don't want to actually get to that situation. Uh, well, there is a solution out there. One additional open source project, Open Policy Agent, that communicates, in our case, with another open source project, OpenFGA, that allows to provide this information to Trino or to whatever engine is out there. Because in that case, we provide the information to a trusted compute that Peter can read, and Bob cannot read. And trusted compute will apply that in this case. So this is how the flow actually goes. Now we will go to the demo. So there's a handle, the demo code. And let me just. So first of all, if you want to run the same demo, there's a repo from Lakekeeper, and there's all the examples. And in that folder, we have a couple of different examples, and I think one is from, yeah. So that's kind of like the way of a contribution to open source. My demo is going to be this one, and everything to do to repeat the same demo, you need just a single command. Docker compose up, and then you're good to go to run the same demo. After the Docker compose up, you will get a couple of things to run through. So first of all, you need to run the bootstrap script, which is like needed to create everything, to make everything in place. The second script is to create the first warehouse, and that's what you will run here. And the first script is creating the catalog inside of Trino. So that actually helps you now to create a catalog in Trino. And then we will get actually to the place where user, in our case, Peter, can run a query. And what Peter is trying to do is now to select a table in namespace finance. So let me just run the query. Here's exactly the authentication, and we'll authenticate ourselves as Peter. Succeeded. Go back, and voila, we've got the data. So just for a moment to recap what has actually happened, it's not a single Postgres where everything is somehow embedded and working all together. We have a highly distributed system. We have storage, we have compute engine, we have catalog, we have policies, we have authorization system, we have identification system. So 5 or 6 different systems that do not depend on each other, which is a kind of a complexity how to solve. And that's exactly the way how you can do it just to solve it. And just to prove it that it works, let me just go and try the same with a different user. Yeah. Now I hope. Let me see. User Anna. Okay. Let's use Anna. Password Iceberg. When Anna used Keycloak in our case to make the authentication, and now we see that Anna has no permission. So that's how system is able to enforce the permission and enforce the access level. So what Anna can do, Anna will just go now to Lakekeeper, sign in and to see what's going on, and you get no access. But what Anna can do now, can Peter, because Peter has access to that data, and ask him just to give uh, her some access to a table product. We'll go to warehouse demo, namespace finance, tables, products, and we'll go permissions, and we'll grant access to Anna and give Anna a select, click on save. Going back to the same query and rerun the query. Make the authentication again. And Anna now is able to query. It's quite interesting because if I will go now as Anna, check the status, now I see that I have access to the data, to the same warehouse, to the same namespace, but I see only one table, where Peter can see 2 tables. So that's the way how you can actually enforce the access from table level to a different persona, to different role-based access control. So if you have a role manager, the manager can see more and less. So that's kind of a tricky part that we have with Apache Iceberg, and I will go back to the slide. So that's a recap where exactly you see all the different components, and still, if we're not in a monolithical box, we're able to ensure that access is not violated, that data is not read by someone who should not read it. But the feedback what we've got, it's super nice. It's all open source and it's enterprise grade security, so you can actually take it and then implement it. But then you need a team that need to understand 1, 2, 3, 4, 5, 6, 7, 8 different technologies. It's probably a little bottleneck usually on a single persona or 2 persona to manage all that stuff. So what we said, let's make it a little bit simpler and try to get rid of some components. And to achieve that, we took open source technology, CEDA policies, and you wouldn't believe me who open sourced that. It was Amazon Web Services, which is quite interesting because Amazon is not that known for the open source, but they did. So it's a very powerful way of implementing the access. But the cool part, Using that technology, you don't need any more of the OPA, you don't need the OpenGA. It is a policy where you can say, like, Alice can read the table. And this is a approach upfront, which means you, as a CISO or data security persona, can just go and declaratively define the state of your data security. So it's not like I'm calling Johan, we have a table, please give access to a person, or please take the access out of that table for that specific person. No, you as a data owner can define exactly the way how the data access should happen. And then that policy will go through your workflow process and will be deployed automatically on, in our case, in Kubernetes, and Lakekeeper can enforce that just right away. And that's kind of a separation of powers. So you have a way where the data security will be defined. Then you have a piece of infrastructure that executes or applies that security, and hopefully you have somewhere observability that can judge, was it kind of okay, what happened or not. So quite similar, probably you know that we call it democracy, right? So we have like executive, legislative, and judicative, and that's kind of a same way of building a system. So that's probably better than have a tyranny in a single box, and then you don't have like any control. So getting back, so what we proposing is to make peace, not to fight, like, oh, governance is in our side, on our side. What we wanna say, like, "Okay, guys, governance is a thing what should be solved some kind of a different way, because all of you provide the compute to solve some specific things," right? So SAP is, first of all, for business processes, really. Snowflake has analytics, Databricks has data science. Well, I don't know what Microsoft Fabric does. If you have an idea, just write to me. I'm glad to adjust my slides. No offense, Microsoft, always good. Yeah, guys, that's it from my side about quite boring topic, data governance. If you liked it and if you want to try it out, there is a GitHub. Visit our GitHub repo. Give us a star. We would love just to collect some stars. We open source. You don't need to pay anything. You can just try it out. That's it. If any questions, I'm happy to answer that. Questions? No questions. Go ahead.
So yeah, so you know me, so not a data guy, and definitely not a five in Iceberg. But I was wondering if when you were looking and learning how to use for did you have to come up with actions as an example that made sense for the catalog? And then I think a follow-up question I have for that is, do you know if from the community, if not really extending the existing specification, but maybe creating like separate standards that would maybe extend catalogs
Yeah.
for the permissions, if that's something that there's someone doing, or if it would make sense?
Yeah. So maybe let's start with the last one, because there are a couple of proposals, and by the way, Apache Iceberg is open source, which means every one of you can go to the sync that happens like every week. You can listen, you can propose, you can develop stuff, you can be very active. And going to the FCAC proposal, there are like different proposals on FCAC, how to make the fine-grained access control. Especially the proposal goes not even just, okay, that's the way how we will secure the table and views, but how can we do the row filtering and column masking as well? So, and here's again the play. You probably remember. Let me just go here to, yeah, here to that one. We will have a trusted compute in every situation. It might be Snowflake, Databricks, it might be Trino, where the policy is stored here. And then it's like the question, if it's on a table level, then the catalog can perform that exactly limitation if you can run, and I not. So you will get 200, I will get 403, so I cannot run that operation. But The nature of Iceberg is if you will download the Parquet file, the Parquet file might have some rows where you need actually to apply the row filtering. So in that case, the Parquet will actually go to trusted compute, and trusted compute needs to apply exactly that PDF user-defined function where we will have like where clause country equals Germany, I can read it, country equals Spain, you can read it. And that is like the play between catalog and compute. It's not just uh, catalog only. But there are different proposals. It takes time to get there. Let's see if we will get by end of this year with FCAC, and then we will have a situation where catalog is primarily in a place to give to a trusted compute. Let's call it the action which needs to be applied, and then every company needs to understand like what is a trusted compute for them. That to me probably is hard to make a trusted compute because that you will download the whole PK file and it's on your machine and you have like the root access, so it's hard. But if it's Trino or other like database Snowflake, it is good. Yeah. And the first one,
If you had to come up with actions how those seller policies, I, as I said, maybe it's clear that the specification for Iceberg REST or just Iceberg would already tell you that, but I was just curious.
yeah. So on that one, you'd need to define a schema. And in that schema, you will define your objects like namespace, warehouses, tables, and then you will define the action. And that needs to map with a catalog that enables to apply that. So if you will Polaris has a different way to do stuff, operations, I guess, than Polaris does. And same on us. So Lakekeeper has some specific functions what you can do with your data. And then we have all the different actions. The cool part is that you can create your own schema for your own use case, either to limit or to extend. And then you can go like take Lakekeeper, extend that to your specific, your company function for whatever reason, and then apply that. Yeah. Wonderful. Then one more. Yeah, AI agents. With all hallucination. Sure, why not? Um, maybe just to give you a quick sneak preview. Let's go that way. So what we have with Iceberg is that we have a structured data. Well, with Variant we have a semi-structured data, but usually we have structured data. The AI agents, like agentic system, they tend to go to the unstructured data. They love to read PDFs and Excels and images and whatsoever, which is not covered for that part at all. And the kind of like funny part is that the structured data is probably like the maximum 20% of all data and 80% is unstructured data. But the good mechanism inside of Iceberg, what we use is so-called vendor credentials. Anyone know what vendor credentials is? So vendor credential is, well, usually if you go to Amazon and you need access, you will create access key and secret key, which lives forever, and you have no idea who is using that. Vendor credentials is similar, but it's just maybe like for 10 minutes or for 1 hour. In that situation, if you as a user will go to Lakekeeper, you will tell, oh, I'm Victor, and I want to read table revenue. So Lakekeeper will communicate with object storage, will ask, okay, Victor is allowed to read a table, please give me the temporary access key and secret key. I will give it to him, and then he can just read it. So long story short, the mechanism that allows us actually to limit access to object storage without giving that long living credentials. So the idea is right now, why not to apply the same mechanism to unstructured data, and then your use case with agentic system will actually use the same mechanism in order to get the access. We can extend that, and then the agents can just go and use a zero trust, just in time access keys to. So yes, extendable 2027. It's going to be open source, and if you want, you can contribute. All right. Then I would say thank you very much, and then we have our next speaker. Go ahead. Let me see. Where's your presentation? Right.
Right. Hope you're ready. Right. Hello, everyone, and thanks for coming. It has been 14 months since I flew, and it was the first time being of a two-person team. For joining, I kept hearing these words like data, 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 but it wasn't until recently that I started to understand the real meaning and the huge amount of work. My name is Senior Data Engineer at Santos, and today I would like to share my experience on how we build a self-managed open lakehouse with a governance layer on top. All right, but of course, before jumping into that story, a little bit about Cantox. Cantox is a software company focused on policy management automation. How I understand it is that we keep moving information. All right, so our first approach to a data platform started with oh yeah, sure. Started with Delta Lake, but after some time, we started noticing that more and more people started to move towards Apache Iceberg. So what really attracted us about it was the openness of the project. We wanted more engines, choices, more flexibility around catalogs, and of course, less vendor locking. Our stack was pretty standard. We had like S3 buckets, Hyperstore, Trino, DBT, and Daxter. It worked, but of course, the business wanted more. So a new data feed came in. It had a throughput of around 5,000 messages per minute. And yeah, the thing is that up to that point, we were pretty much batch oriented. So we took this as an opportunity to actually upgrade our architecture and introduce Kafka in our stack. All right. So our producers, the platform team, they already had RabbitMQ in place. And since we didn't want to disrupt too many processes at the same time, yeah, we just told them, hey, just send us the events in a queue and we'll take it from there. To make that happen, we set up a source connector. So now we are moving data from the platform to Kafka. Now we have to do a second thing. We introduce the Iceberg sync connector just to stream the data now into our lakehouse in an Iceberg table format. All right, so I mean, this looked nice. It was a solid plan, but then I hit the first wall. I remember I've been working on this POC for about a week. And as soon as I wanted to move this into staging, yeah, I realized I have Hive Metastore version 4.01 deprecated the get table method. And unfortunately, yeah, Iceberg depended on it, the Iceberg connector. So that left me with in the following situation. Option A, we downgrade and freeze our Hive Metastore to an older version, pin every dependency, and just hope that nothing else breaks. Or we move to a REST catalog. I mean, we've been already talking about this, and we wanted to do it anyway. So, yeah, why not, right? Why not spending the next 2 weeks just understanding what's a catalog, what are their trade-offs, and I mean, it was July in Barcelona. Who needs to be outside enjoying the sun, right? When you can be at the office and doing a catalog migration. So long story short, yeah, we went with Gatekeeper. Uh, the documentation super clear, examples exactly what we needed, and they were aligned with our vision of the lakehouse. Also, no JVM. And man, like for a team of 2 people, that's a huge relief. Finally, they were open to contributions. Yeah, super welcoming from first minute and always helpful. And I mean, at that point, I said, hey, I want to give something back. So that's why I prefer the Iceberg Sync Connector example and open a PR. And luckily, thanks, Victor, it got merged. All right. So it has been 6 months of hard work, learning new technologies, and actually putting every piece of the lake house together and make it fit. I wouldn't have thought that this would actually turn out to be the easy part because now we had to think about governance. So today we have different type of consumers. We have humans, AIs, AI agents, LLMs, dashboards, and yeah, the thing is that no matter what type of consumer, you all need to follow the same rule. You only get to see what you're allowed to see. And for this, yeah, here's how we tackle the challenge. Our approach had 2 main parts: the IDP, the identity provider, and the data contracts. The IDP is basically where we create all our users and organize them into groups. We have 3 of them, 3 types, yeah: customer, internal, and external. Each one follows a specific naming convention. For customers, we look, that's all. Okay. For customers, we attach the UID to the group name because we're going to use it for row level filtering. We also define an access label, which will tell us, hey, what these users can do on a table. In this case, it's set to viewer. For internal and external, the problem is a bit different because we don't apply row level filtering, but we still need to care about the sensitive data. And for that, we introduce a new user attribute called the classification level, which it will help us to mask certain columns depending on, and here's where data contract comes in. The data contract, it's important because the domain that owns it defines which roles can access to that table and how each column is going to be classified, either public, restricted, or confidential. So this is how it all connects. Let's say we have we're onboarding a new group, and we have our CISO, Jeremy. Is not here? No, not here. Jeremy accepts the procedure. We immediately create a new group called BDR, for example. We add a new user, Lucas, and we assign Lucas to BDR. So once this happens, Laykeeper is going to mirror what Okta just did, just to um, realize and know, be aware of it and match their relation. They still don't have any access to the table. For that, we need to move to the contract side. So now we open an NPR, we define our data contract, and there we say, hey, grant role BDR, select permissions on table A. Once this PR is merged, our CI/CD will kick in and will trigger our internal service called Waffle. 2 things are going to happen. The first one is going to tell Laykeeper, hey, you can give access, select permissions to this table, table A. So at that moment, the group BDR is able to see the table. The second thing, it's going to generate a set of legal policies, which are going to be pushed to the OPA server. Here is where the row filtering and column masking logic actually happens. All right, so, oh, let's see a demo. Yeah, I had to record it. That one. Yeah, I can do that.
Here, online. You need to click.
Yeah.
Right. Perfect.
Perfect. Hi, everyone. My name is Miguel Sotomayor. I'm senior data engineer at Glassnode. And today I'm going to share with you the amazing journey that we have with Apache Iceberg and Glassnode. Okay, so let's get started. So first of all, yes, not very good. The presentation. Okay, that's fine. First of all, I'm going to introduce a little bit about Glassnode. What is Glassnode and what we are doing? Okay. So in Glassnode, we are a company which is basically producing advanced on-chain and off-chain advanced metrics, okay, for crypto assets. Okay. In particular, our main customer might be, for example, traders, investors, and researchers as well. Okay, and today probably we are going to be more focused on this part, which is okay. Once we have the data in Apache Iceberg, how can we share the data with another entities, and other layers, and other technologies? Okay, that's exactly where we are going to see today. Okay, so for example, this is an example of our web application, Glassnode Studio, okay? And here we can see an example of a metric, and this metric is this kind of data that the consumer are consuming, okay? Not only via web application, but also, for example, we are sharing information using an API. So customers can use an API just to get these metrics that I mentioned before, but also we are providing historical data through BigQuery and Snowflake all together. So here the key is, okay, once we have all of these metrics that we are providing in Apache Iceberg, how can we share all of this stuff efficiently through all of these platforms? Okay, and that's the key. So as I mentioned before, this is an example, okay? And basically, we have what we had before Iceberg and with Iceberg. Before Iceberg, what we have is exactly, well, we have all of these metrics stored in Parquet files, okay? And these Parquet files, we were running some kind of custom logic on top of these Parquet files, for example, to apply inversioning or to enrich this Parquet file with metadata, okay? But that was not enough because all of this stuff had a lot of problems. One of the problems is something that Victor mentioned before, interoperability. For example, Snowflake didn't know how to read this custom logic that we built on top of the Parquet files. Was not possible to do that. It's also true that, for example, as I mentioned before, we have an API built in Glassnode. Yeah, that API was able to connect to extract the data from from Parquet files. Okay, but we cannot connect BigQuery, Snowflake, or any other third-party tool. Okay, and that's because we decide, okay, let's go to Apache Iceberg. Okay, and basically, one thing that we need to take into account is a data challenge that we have at Glassnode. Okay, we have a lot of metrics. You can think about a metric like a Apache Iceberg table. Okay, a metric is a table, but it's not 100% true because one metric has different granularity. So at the end, we have a lot of different Apache Iceberg tables. Okay, and in terms of volume, for example, we are generating around 500 or 600 gigabytes per day, more or less. So it's a high volume. So yeah, the point is, how can we manage all of this stuff, right? So Apache Iceberg, I think it's a way to manage that. This is high-level architecture. In our case, we have many more components, but just to simplify this talk, we can think that in terms of source, we have Snowflake, data in Snowflake and BigQuery. We have some jobs in the middle. We have dbt running in Snowflake and BigQuery. We have Spark jobs. transforming all of this data in metrics, okay, in Iceberg tables, okay. And once we have Iceberg tables, here probably is the important thing. With the same tables, we can expose this data through different technologies. So the API will consume the same table than BigQuery. Snowflake will consume the same tables. We don't have replication. Okay, that's the good thing. The first thing that you can think, for example, is that saving costs, right? Because you have the data all in one place, right? And usually this place is more or less cheaper because we are storing all of this information in GCS, in the Google Cloud platform. Okay, great. So let's start with Snowflake and BigQuery, the data warehouse. They are similar. Well, it's not the same. There are a lot of difference between Snowflake and BigQuery. But yeah, finally, it's just a data warehouse. Okay, how we are sharing that information with these data warehouses? One important thing is that we are not replicating data. Okay, all the data is in GCS, in Apache Iceberg tables, but we are not replicating this data in Snowflake or BigQuery. What we are doing is creating external tables pointing to the Iceberg tables. And here is one difference between Snowflake and BigQuery in this sense, because in Snowflake, well, first of all, I didn't mention that the catalog that we are using, unfortunately, is not the keeper, sorry. At this moment, it's a Snowflake Open Catalog based on Apache Polaris, okay? Based the catalog that we currently using, okay? At this moment, BigQuery, okay, is not able to detect changes automatically in the Apache Iceberg table. So that means that if you execute a write, if you create a new snapshot in the table, you need to manually say to BigQuery, hey, point to the new metadata file in Iceberg. Okay. Obviously, if you use the catalog of Google, it's automatic. There is not any problem, right? So in Snowflake, it's a little bit different because you can point to a REST catalog in Snowflake, and Snowflake is running under the hood a job at SnowPy, which is basically checking if the table has changed. Okay, so it's easier. Okay, not cheap, but easier. Okay, okay, nothing is free. Sorry. Um, yeah, so basically, this is the picture that we have with data warehouse. I said before that we are not replicating data, okay? Not 100% sure, okay? Because Snowflake, if you, for example, Snowflake, if you want to share your information with another regions, Snowflake is mandatory to replicate that data in the region where the customer has their Snowflake account, okay? And that's because internally Snowflake is replicating data. That's something internal, okay? For example, if we wanna share information only in one region, we don't need to replicate the data. It's just a external table pointing to the Iceberg tables in this case. Okay, great. What about the API? Here is a little bit more complex. Okay, I need to say one thing before continue, is that the data that we are storing at Glassnode basically are time series. Okay, for example, something super simple. The price today is 28, okay? 28th of May at 3 p.m. The price for Bitcoin is, I don't know, 70,000 euros, okay? Hopefully. And well, it's basically a time series. In 1 hour will be different. So basically, all the metrics that we are exposing to customer are time series. It's important because what I'm going to say right now is it's important to have into account that. So in the API, the picture is different to the data warehouse because when you have historical data in data warehouse, probably the latency is important, but not super important. Here in the API, the latency is super important. Okay, so one more second in the request of the customer is significant. Okay, so that's because if we are sharing information using the same table, maybe we need to adapt our information to the API because we have special requirements here, especially for the request time, right? For the latency. And what is the problem of the latency? Imagine that I have one table in Iceberg with one file, 10 megabytes, okay? And basically the customer is going to request that information, the whole table. So basically, what we need to do is to read 10 megabytes. And that's something mandatory. That's something that you cannot avoid, right? But what happened with the catalog? Every request, you need to ask the catalog, hey, where is the information? Okay? The catalog takes time to respond, right? So when we are talking about milliseconds, okay, that time matters, okay? So the key here is just to try to reduce that time, okay, as much as possible. And we have different options, we have different strategies to try to reduce that latency of the catalog, okay? One of the options, caching. We need to cache the information, okay? So what we have in our system is we have the API, okay, in our side, and between the API and the catalog, we have a proxy. And that proxy is storing information in our Redis, okay? It's true that for us, it's really easy, for example, to invalidate that cache because, as I mentioned before, we are responsible to generate our Apache Iceberg data. So, for example, if a new data is coming for a table, we can send a message to the proxy saying, hey, invalidate this entry because there is a new snapshot. Okay? So caching, the caching is essential for us. Okay? Metadata reduction, also super important because, for example, by default, when you create an Iceberg table, automatically the system is going to gather statistics for all the columns. I think there is a limit. By default, it's collecting only the first 100 columns, okay? There are a lot of columns, a lot of statistics. So that means that the metadata is growing and growing, okay? That means that the request to the catalog probably will be slower. So try to keep this metadata as low as possible. Okay. In our case, for example, as I mentioned before, we have time series. So for us, it's super important to have statistics by timestamp for the column timestamp. But there are a lot of statistics for a lot of columns that we have which are not useful. Okay. So you can remove it. Okay. You can configure based on table properties in Iceberg that you need to collect only specific statistics for these columns. You can configure that. Reducing partitions is also important. We notice that tables which contain a lot of partitions, the catalog, the request to the catalog will be slower. Okay, try to reduce as much as possible as well. Selective compaction. This is something that we are doing, but depends on how your customers are consuming your data, okay? Because in our case, as you probably know, if you are working with Apache Iceberg, there is a moment that you need to compact information, right? But for us, uh, we are compacting the information not always and not on the whole table. Why not? Because we realized that we were analyzing the behavior of the customer in our case. And we realized that the customer used to request the most of time recent data. We are storing historical data, but most of time they are requesting, I don't know, recent data last hour, last day, okay? So we need to prioritize this kind of read.
So that's because we have hot partition, recent data, cold partition, historical data. Okay. But in the hot data, we realize that it's not super important to compact information. Even more, sometimes it's better to have, for example, small files more than bigger files. Okay. Even better, having small files or multiple files instead of having one big file, you can parallelize the reads. Hmm? Especially if, for example, if you have your Apache Iceberg table sorted by a column. In our case, remember, we are storing time series. In our case, we are, for example, having all the tables sorted by timestamp. When you create a table, you can specify how that table is sorted by timestamp or by multiple columns. In our case, tables are sorted by timestamp. So that's really nice if you have a parallel process reading small files at the same time for one specific query, just to find the time range that the customer is requesting. Okay? But again, this is in our case. Probably your case will be different. Okay? But for time series, this is something cool. Okay, this is, for example, one chart where we are showing the response time for a specific request. The red line is the time of the catalog right now with all of this enhancement, 15, 50 milliseconds. Okay, it's true that this is for a small table. For bigger tables, it's a little bit higher. Okay, and the red line is the time reading the market files in the Iceberg table. Okay, the yellow line was the previous was the war before Apache Iceberg. Okay, yeah, that's the difference. So the catalog time is always there, but what we try to do is just to minimize the impact in the request time. Okay. And yeah, so basically, for example, this is the configuration that we have in our tables. It's the general configuration, not for all the tables. That's what I mentioned before. We are collecting metrics only for the timestamp. We are keeping our metadata uh, really small. For example, only maintaining a snapshot 48 hours. But yeah, all of this stuff is going to depend of your case. Okay. Copy and write, super important for optimized readers. It's gonna be slower for writers, but much better for readers. Okay. And yeah, that's all. Thank you very much. Questions? Yes.
So can you go back to your architecture?
Yeah, sure.
You were using Iceberg tables for that. Yes, like it moves to Snowflake. At that point, it's moved to proprietary.
Actually, is external Iceberg table the right concept in Snowflake? Yeah.
Okay, so you keep using Iceberg.
Yeah. Mm. But it's not internal because in Snowflake you can have internal Iceberg table or external Iceberg tables. Yeah.
But it's still Iceberg.
It's still Iceberg, always Iceberg.
So and another question.
Yeah.
So your this last part that you covered, the real-time API.
Mhm.
So you talked about like small files and stuff. What are you using for serving? Because if you're doing any analytics over there, you use like a Spark or something like that. Sure, you can prune a lot, but if you have to like metadata for a lot of small files, that's not very efficient.
Well, keep in mind that when you are accessing to a table, you need to keep it small. Yeah, I know your point. Yeah, but keep in mind that imagine that you are reading the example that I put before. You are reading 10 megabytes of file, okay? But imagine that that 10 megabytes of file is 1 day, but the customer is requesting only 1 hour. You need to read 10 megabytes if you have only one file. So the time reading 10 megabytes probably will be slower even if you have more metadata file in the catalog.
Yeah, but 10 megabytes is small.
It's just an example, right? Actually, our whole data, sometimes we have 10 megabytes, right? But here we have much more, even more than 20 megabytes. Okay. Mm. So if you compare 10 megabytes with 8 megabytes, it's more or less the same, right? Thank you. Right now, the data quality that we are managing is especially in previous steps here. So one thing that I mentioned before is that we are running DBT, okay, apart from Spark, and we are performing some kind of test in the DBT to ensure that the data, because it's just two sources, we have more sources, right? The data that we are producing, the metrics that we are producing are okay. Okay?
Just curious about the use case of the real-time API,
Mm.
because I am very interesting to manage to try to see request real-time API loop. But I'm curious about the use case of how you're using that API, and also the process that it takes for data to become available in the real-time API is important to.
So basically, the users, and not only the users, this one is also using the API, right? So basically, uh, there are many different use cases. There are use cases where you are requesting small portion of data, which is basically this one, okay, that you can see in the chart. But also there are researchers or investors, even traders that are running algorithms with historical data, okay? They are not using a Snowflake. We can provide also a Snowflake and potentially more in the future, but they are also collecting all the data from the API as well and just running a specific algorithm. That's because that's the complexity of this stuff. So we have many different customers requesting many different things at the same time. So again, it's also true that we need to analyze what is the behavior of the customer. Okay, we realize that the most of the time they are requesting hot partition, but not always. So we need to be ready to serve all of this stuff at the same time. It's also true that when the customer is requesting a big portion of data, okay, probably this time is not so important because the request is going to take seconds. The problem is that when the request is just with a small portion of data, okay, you cannot spend. At the beginning, we were spending, before all of this enhancement, we were spending 1 second in the request of the catalog. That's of all.
I wanted to understand if you have identified customers and you probably spend some time to feed data from your sources to the developer.
Mhm.
And I'm just curious if there is a use case for a trader where they would like to get the data fresh as fast as possible. As soon as you get it from the source, as soon as possible to get it in the API.
This is a problem actually. The latency that we have, the lag that we have from the source until it's ready to be consumed for the customer. This is a big problem for us, especially where we are talking about, for example, small granularities. Okay, it's a challenge for us. Yeah.
For the API gateway microservices part, just a clarification. You are not using any database on top of the catalog, or is there a
No,
case?
Redis for caching, just Redis,
Yeah.
nothing else.
Can be, they connect.
Mm. Well, not 100% sure because just because the legacy system that we have with Parquet files, when we were using Parquet file, we were using Postgres to maintain all the metadata. And right now, we are storing small portion of the metadata in Postgres, but it's something that is gonna be deprecated soon. Crossing fingers. Okay. More
Uh,
questions?
Maybe just question from my
Yeah,
side. So
sure.
the microservices, can you just describe how exactly that actually is implemented? I mean, I understand you need to transfer the whole parquet file, but you don't need to read the whole parquet file because it's smart format. That's one question. Have you considered to replace parquet with LUNs because it has random access?
It's an option. Actually, we have a lot of challenge in terms of the file format as well. We also consider Delta Lake that you was discarding at the beginning. So yeah, we are open to that because sometimes even depending of not only for random access, but also right now we are quite happy about the response time. That's not a big problem. Our big problem right now, or one of the problem, is that what this guy mentioned before, this journey. Okay, for 10 minutes resolution, sometimes we are on the limit right now. So that's because we have a lot of challenge just to improve all this stuff. But in terms of request time, I don't have right now a motivation to make a replacement. Yeah, but yeah, that's an idea.
On Iceberg, it's probably not a replacement. If you're aware, there is a file format.
Yeah.
You read the laws, if you take different months or vortex, a different format, and
Mm.
for different use case, and therefore you can still stay on Iceberg, but you can build your own file format for your specific use case.
Mhm.
So okay, so I understood the main challenge is here. So is here a source system directly, or is
Yeah, a little bit more complex over there because we are also consuming
all right?
different sources which at the same time are publishing in BigQuery. It's a mess. This part is a mess. Believe me.
Then it's probably a longer discussion. I don't want to like hold you from like tasty stuff, and therefore Miguel, again, thank you very much.
Okay.
And now, guys, we have 30 minutes to digest everything what was presented and take something what is tasty. So enjoy the next 30 minutes, guys.
Hi, good afternoon, everyone. Where is
have a
the?
clicker?
It's here. Okay, where I am from ClickHouse. Any of you know more or less what is ClickHouse? Mm, yeah, that's good. That's good. Then let's start with quick. My name is Jimmy, and I'm a core software engineer from the core team in ClickHouse. So I'm not a product or sales or so. So I will try to make the speech a little bit uh, mm, interesting but not very technical. It's possible. So what is ClickHouse? It's an open source OLAP database. Basically, it is very efficient. It is raw storage oriented. Our silver bullet, to call it somehow, is the storage system we have. We use something called merge trees, which is an infrastructure that allows to make very efficient computations over the data using vectorized and many optimizations, multi-threaded. The level of optimization is very high, so we can ingest millions of rows per second at the same time serving queries. Everything concurrently. Essentially, we speak SQL fluently. We process data very fast with high efficient storage, not only for the access but also for the compression. In many cases, we get more than 10 or 20x in save in storage. Just automatically, you don't have to do anything. It's out of the box. It's our automatic compression system, and it's very easily scalable to any time. We have a very strong ecosystem integration. Usually, you have ClickHouse as a center of the database. You have in sequential in a single instance or in parallel. We have many applications or clients asking data. Then we have integration with multiple tools, like for example Grafana or many other tools that we can share information with. We have agents and some others. And in the other side, we have also the storage, and when that we are ready for many different kinds of storage, data lakes with Iceberg, and we support basically all the major supporter or the major companies like AWS, GCS, or Azure. Essentially, at the moment, the company is centered in providing data or find ways to provide good data and in an efficient way for modern data teams. This includes not only the big flow of data that the modern system require, but also agents and all these systems that we are already serving. We need to have a speed. So the real time inside, we need the very fast sub-second queries. Many cases we need to scale because not only the data but also in the access, the number of clients and the number of storage. We need to be efficient in cost because this efficiency in energy is something that saves us in the side of the total revenue that we get. We need also enough flexibility from outside in order to create more products and for the client. A unified view, which is the user should not take care about the inner details of many data. We try to provide for the clients the most transparent experience we can without making them to give more to take care about the inner details. Of course, this has some trade-off because at some point you have to order your data or modify your queries in order to be efficient. But once it's efficient in one shape, then we can scale at any scale and it will continue being very efficient. And finally, we have to support agents which has a very different very different kind of access to the data because usually the agents access a lot of data, not very predictable pattern, and we have to take care of all of that. So one of the top priorities we have is performance. If you look at this table, this is how the average performance in ClickHouse evolved from 2018 up to now. It looks like it's almost 2x. This doesn't look like too much, but if we consider that the baseline, which was this point, was already very fast, is a very good thing. Also, this is an improvement in average. We run some benchmarks like ClickBench, MGBench, and some others, and we execute something called version bench, which is every time we have a release, we execute all these benchmarks and we compare with ourselves and with other baselines that we have. But for example, in some specific cases, we have speed ups in the order of 50, 100, or 400x compared to last year or previously. So if you want to access the ClickBench, you have the screen there. It's public. We have all the data public. Compare our database with other databases, and even them publish data in our page, so you can compare the different with different platforms, different systems, different queries. We have more than it's 42 queries in ClickBench right now, and it's about 100 million rows at the moment. So as I said, the priority number 2, because the priority number 1 is reliability of the system, the priority number 2 or second priority is performance. Is what is the most important, is a very important one. And the trick is how we archive that on top of Iceberg. And we have we lost some configuration converted to PDF. ClickHouse has the basic integration. This is something very old, like 2-3 years old, which is the Iceberg function. The Iceberg function allows you to access Iceberg tables, accessing through the catalog, a snapshot manifest, read the data, and it's basically the simplest way you have to access the data. So usually what happens, why we do that? Because as I said, one of the things that we have and is very efficient is our internal storage system, which is we call native, which is the merge tree. Merge tree is very fast, which is this yellow line that you have here. You see that in a core room, it is almost 2 times faster than accessing directly ClickHouse plus Iceberg. And usually the same query in merge tree, once you have a hot room, is way faster with the internal ClickHouse system. So the point is, we cannot copy all the data into our database every time you want to do a query. We have to optimize over that, which is logical and is something that satisfies. However, if you want to access a lot of times the same data again and again in your table of multiple analysis, or is data that your user or your client needs very frequently, this workflow is still good enough because it gives you access once, so you read once, and that's it. Where is the problem? So we want to have more integration with the Lakehouse, and this has to make the compatibility house. So we have we have to have access transparent to open table formats like Iceberg, Data Lake, UD. Catalog support, we have to be compatible and transparently compatible with file format, and the authentication and permission system should work. And this is basically the main goal. Don't provide any extra layer, any extra process, any extra plugin. So the user could use the system, so could use ClickHouse to access all that in a transparent way, in a documented way, and in a way that you can support without adding extra complexities or extra costs. So that's why we need to have to speak natively. It's not creating a wrapper or creating an extra layer. Is to be natively accessing the data and also apply our optimizations directly into the system in order to take advantage also of them. And we also need to make it fast. So we need to do file format optimizations. We need to make optimizations in the tables. So in order to apply filters and projections and different layers, we rely very heavily in parallelization. So we also have to do that. And finally, we need to do caching. We can do caching transparently for the user in order to save the user some time, and the user doesn't have to implement this caching of certain parts in order to reduce latency here or there. We already implement that, and every time we find a spot that we can optimize because it's a frequent or is a bottleneck any pattern that we can imagine, then we can optimize that. If it requires a caching, it requires some optimization, we do. So at the moment, we have full Iceberg version 2 specification support. So we have end-to-end read and write. The write version is something that we have added relatively recently, about 6 months or so, but it is very well tested at the moment. So we can read, which is the common. Remember, usually systems like ours tend to use this the storage as a cold storage, so a place where you put the data and you keep the data there, and then some other source stores the data. So basically, they use the OLAP database to access to read, but not to write. And we have implemented the full write support, including insertions, including alter tables, and everything. We have a quality and positional deletions, which is something that I think is released already in the beta. We have automate compaction, which is, well, you know what is compaction. We implement in 2 ways, so the user can control the compaction, but there is also some compaction that happens automatically depending on some settings in the system in order to not force the client or the user application to need to take care of these details. We have the full Iceberg V2 specification. So we have a snapshot. For example, when you insert data or you alter the table or whatever, you create a new snapshots, and these snapshots update everything in order to use, you call it time, like a time machine. I don't remember what's the real name. And we also have the integration with the geometrical types. This that also have now the parquet, which are the lines and the geometrical things, polygons, and these things. We already have native support on that. This one is something that I like very special because ClickHouse has a lot of functions for geometrical processing, and all these functions are already compatible natively with these types now without an intervention. Of course, with the initial function, that was not enough to perform this because you cannot read, then you forget what you read. So now we have the Iceberg table engine, which is a table engine. Is like you create a sort of table in your system, but you say that your storage is an Iceberg storage. So this is totally transparent for the user. It's like creating a normal table. You can see here that you create a table, you name it, and you say where is the storage. And that's it. Then you can SQL normally, like any table on the system, and you can access directly your data there. There is more integration where some data lost here. You see the lines here. You can do the select with the Iceberg table, limit, whatever. And with this same table, you can also insert data. You see, you allow insertions, and then you insert data into your table. The system takes care of insertions and synchronization, updating metadata, and so on. What's the point of this? This allows us, as you are creating a table for your system, so for a view, imagine like a view that you have for the real system, this makes you, it's not like a read and forget as it used to be, but it's a read and remember. So you can do many caching. So for example, in this case, you can cache all part of your data, so the snapshot, the manifest, and the manifest file, and you can synchronize them internally. So if, for example, if you have the same instance inserting data and reading the data, I mean the same server, but from different clients, then so most of these operations don't go directly to the storage, so they don't have to pass or the pipeline forth and back, but they are happening in memory. And in the back part, so at some point in the back memory, somebody synchronizes the hot storage in case some external application needs to access it. This happens almost immediately, of course, but it requires some extra optimizations. One of the things that we celebrate very much is that this access, as you can see, is not only for read, it's also for write. So you can also use ClickHouse, you create the table. Once you create, you can create not only a table in ClickHouse, as I showed in the preview, you can also create a database as a data lake. That means that you create a database as a data lake, and when you write or you create tables in this database, this table is automatically created into the Iceberg storage finally. So when you're done, you're done. The user doesn't have to do any extra external plugin or anything. So we can just write the table, and we can update the Iceberg table and analyze your table metadata. So we run 40% faster. We run 40% faster since version 25.9. So this is November last year. This 40% faster is compared, I mean, you can see this is the baseline, so the original version 8 months ago. This is who we are now. And this thing you see here is the native. So it's our internal merge tree compare, which is, as I told, it's very efficient because it has been developed for almost 15 years only to do data analysis. So you see where the comparison with call and hot and cold room. And basically, this will be the last slide. We have smarter reads in the optimization we have made this month. We have a smarter reads. So we read Parquet. We use Preware, which is a version to step the different filtering. So we don't have to read all the Parquet file or all the files. We have different steps in the filtering to only read what we really need. We have improved the caching. So we cache metadata with SLRU, depending on the data you are accessing. This works very fine. Actually, we are improving some part of this. The sizes of the caches and so on can be improved. And we have also less waiting because we have parallelized how we read the metadata, depending on the requirement of your request that you do. Where this is basically the explanation of the Preware, where you have a query like this. This is very basic. So instead of reading all the columns in order to make perform with steps, so we only read column C in a Preware step to reduce the data, and then we filter the parts and the granules that we are going to read in order to only read the data you really need to serve the data in the final query. We have a Parquet footer cache, which is another optimization that we have in order to reduce how you have to access the data in order to request the Parquet footer to see which part of the Parquet you have to read. So once you read it once, we cache part of this information in order to reduce if there is a recurrent request after it. And you can see we also have a new Parquet reader, which is very relatively new, but it's very fast. It gives a very good performance in our storage, but in this case, you see that the benefit doesn't look like too much. We are not reducing that much as in you look, especially not in the hot case compared to our case. And basically, we have the metadata cache, which is essentially one of the good things that ClickHouse has is that all the logs, all the system, all the information, all the metadata is also stored internally as a table. So you don't have to read extra files, look externally or whatever. Everything is stored internally. So if you want to look at the metadata of some table that you have or see the statistics of some query, you get all this information in a system table internally. So as a SQL, a native SQL. So this is basically for example, how you access part of some of your information in the system. So just look at the logs and you can read. Actually, in our case, we know where this time is going, and we are still looking how can we handle that because it's out of our control, because most of this time is going into the reading time from the metadata from the storage. So it's the request, the latency, and then managing this metadata internally. So it's totally out of our control. And that's basically it. Thank you very much.
Right. Thank you very much. Any questions? All right.
Just a quick one. I'm wondering if it is a goal for you at ClickHouse to make the performance of the engine against Iceberg tables as good as you have for merge trees, because now there is a gap that you mentioned. I'm assuming that it's even achievable. Whether this is something that you as a company want to do.
Well, let's say in principle, our goal is to get the best performance we can from the Iceberg as it is. Actually, as I say, we have compatibility with version 2. There is already version 3. once we get compatibility with that, we can take some advantages from that form for those new format. I actually was talking a while ago about some things that are going there. There is already people working on that. So of course, the problem is that in our case, is like when you buy standard clothes. So it never fits exactly in the format that you need. And all the ClickHouse platform, for example, the functions that you execute, they are designed for one specific data layout and some specific data accesses. And they are very optimized for that. That's why they are very efficient. It's like when the people compare a standard system with some personalized custom system, I won't mention any name, and they say my phone is faster than yours. This is why. I mean, we have defined this merge tree. They are very efficient because it's not only executing the query, it's also data ingestion, which is very tricky thing. For example, if you add an index for a table, and this index for this table needs to perform too many actions, then potentially your data ingestion is affected, and you will probably benefit the query of the select query, but then you will affect the insert queries. So it's always a trade-off. We are trying very hard, actually. We are doing some caching, and there are many ideas on how can we archive that without affecting without having to intervene too much or customize or forcing an open standard like Iceberg to be made ad hoc for us or ad hoc for some of our use cases. We prefer to go in the opposite direction. So there is a standard, we make proposals, whatever, but something that could be useful for anyone, not only for our specific execution workflow.
Perfect. Then thank you very much for your
welcome.
presentation. Now we are.
Now we're going to watch Netflix, right?
Okay.
Yeah, you know, like if it's your presentation.
I think it was just working, sir. No. Wait, entire screen. Give me a second. Don't press. Yep, that works.
Aunque hagan muy presentaciones, siempre te pone nervioso.
So, I'll rotate it a bit.
Ты надо шарить его.
А?
Он не шарит сейчас.
Не шарит? Screen share. Давай. Да. Шарит. Это должно быть. Получилось, да?
Да.
Okay, so I also put it so that I can see what I have on the screen. Hello, everyone. Very nice to be here. And this office, this is the best view the office can have, literally. My name is Elena. I'm actually here on the way from Germany to Italy, so happy to be in Barcelona. And I would like to talk to you a bit about data. But before going to data, I actually wanted to touch a topic of geology. And it's a sad part that no one really asks me to talk about geology at my sessions. So I'm using any opportunity. Do you know how those columnar structures are formed? Do we have any geologist hobbyists here? No? So sad. Anyway, so it requires a bit of temperature, and usually it's lava, and then some certain conditions under which lava should cool down, so that it's kind of a constant temperature going down, and then it will crack under 120 degrees angles, because it's kind of a nature way to easily crack or easily like form shapes. So, and I recently was in Iceland, and that was the day or couple of days after they had a big volcano eruption. And for me, it was such a huge, magnificent event. For locals, it was just Tuesday. They have it more often than any other country. Somehow vanished, but it's okay. So, and when I was there, I was thinking, so I work at Confluent, so I work a lot with Apache Kafka, and also we work a lot with Iceberg right now. And often we have this use case where we move the streaming data, that hot data which is about the current events, into Iceberg, into more structured data which have those columns, which has metadata and a lot of other attributes which we have. And for me, it was like moving that lava state into more solidified way. And I wanted to share generally the learnings of my team or our company, how exactly we move the data at Confluent behind the scenes, and also talk about the challenges and give some more examples of how other technologies do that. How many of you work with streaming data, and especially maybe Apache Kafka?
Well, yeah.
Well, cool. Anyone just like never worked with Kafka but knows what it is? And anyone who like doesn't know anything about Apache Kafka and thinks that right now I'm talking about poetry or like the German author. No? So Kafka moves the data usually from point A to point B, and then Iceberg, I guess you're already familiar with. So, and when we are talking about the streaming data, it has a totally different format than a data lake. So in streaming data, we have the sequence of events. So for example, you are making a purchase, and then there is like event of which goes about the transaction which is happening right now, and then you need to do some processing on that transaction. But then eventually you want to move the data to data lake. But because the process, those kind of a structure is so different, like we go from events to the data lake table, the basic components are also quite different. So we go from those granular events, which is kind of immutable log of data, into something which is more structured like a table. So, and that's where the challenge is, how we convert those, or how we combine those two different realities. One is kind of this hot flow of data, and another one is more like structured structure. And there are different options, and this is not even all of them, which I have found at the point of creating or of this presentation. So it's a pretty common challenge of putting streaming data into Iceberg or into a data lake format. But I selected several of those options to talk about and to demonstrate the challenges which we work with when we move streaming data into a data lake. And I selected Apache Flink SQL. Anyone familiar with Apache Flink here? Great, we have some hands. Amazing. So for those of you who are not familiar, Apache Flink is the engine which transforms the streaming data. It's a very powerful platform. Then I selected Kafka Connect as something which is also very common to use for any integrations with Apache Kafka. And then I selected Confluent Tableflow because this is where the expertise of my company is in. So like to share just kind of an angle how exactly we are dealing with that. And the first challenge when we need to move the data, and in general when we work with the data, is more or less the scheme of the data. So understanding which properties we have and how those properties, like when we move, for example, the records, we often in Apache Kafka, we often change those like records often evolve as business rules evolve. So because nothing really stays usually as we plan initially, we want to add some extra properties, delete some properties, maybe change the format, and so on. So when we work with the streaming data, it's very common that we would change the schema of the records. However, for the Iceberg, those changes are not always welcome, because you can imagine if you changed the format from, I don't know, from a string to a number. So like there is a limitation of how we can widen those changes, for example, to a property to still make sense for analytical queries. So we want to have a stability when we move the data, and that's why we want to limit those transformations and what you can do, so that we still have a consistent view on the data, and we still can have like over time to read and make sense of what we have in the data lake. And different technologies would do it differently, but if you would have to create it on your own, you might want to rely on some kind of a common source where you have that schema of a record. So, for example, schema registry. Anyone uses here schema registry? So. Cool. So schema registry would be like that place where all the information about the record is stored, kind of a truth. And then when you get the data from Kafka, and you also have somewhere the schema which you use for Iceberg, kind of this schema which kind of the final schema which encapsulates all those changes. And when the schema changes for the record coming from data streaming, you will have to alter table on the data for Iceberg, implement the rules for data evolution, and also keep in mind like this compatibility rules, again, like what is compatible through Kafka and what is compatible with Iceberg evolution. Because with Iceberg, you just, if you want to change the property, like from, again, like maybe it's a stupid example, from the number to string, then all the queries you will have downstream which expect number would be breaking. So you have some kind of limitations there. So you will have to take this all into account, detect automatical schema changes, block what is incompatible, and generally like take care of when things go wrong. And now when we look at different technologies, we have Apache Flink, which it will be the constant theme for this. Apache Flink is the most flexible, the most powerful solution. However, it's also probably the solution which requires the most effort to create and then to maintain. So with Apache Flink, we can control in a granular way how we define the table, how we move the data, and control also the schema. But you will have then, when you evolve, you will have to stop those queries and then to restart it, taking into account the new changes. Apache Flink has all the necessary ingredients for doing that, but it doesn't mean that it's easy. Kafka Connect is more simple in operating and using it. However, it has more limitations. So it's more like a default behavior of the connector. So then you rely on that. And if that is enough, magic works. Everything is kind of out of the box. And it has some the transformations which you can do also with Kafka Connect. It's not that many things which are flexible. But for some use cases, it's actually more than enough, and it's also a good choice. And then how when we started implementing it, we decided we want to have this kind of alignment, and generally we like rules at Confluent. So we defined the strict rules, what is allowed in the schema change for Iceberg, what is not allowed. And then you decide either the record which doesn't fit those rules goes to the dead letter queue, it is suspended or skipped. Yeah, so it's kind of essentially, it's not as flexible as Apache Flink, but it has kind of this predicted mechanism of behavior. That was our approach. The second challenge, or the second thing which we need to think when we convert the streaming data into the Iceberg table is generally like layouts, like the map of the data. And in particular, partitioning. And partitioning, like many other words around Kafka, and around Iceberg, they mean different things in different technologies, because technologies approach data from different angles completely. So for those of you who don't know much about Kafka, in Kafka, our goal is to stream the data in parallel. And for doing that, we stream it in different partitions. So physically, the stuff on the disk is actually written to partitions, which are different files. And then this is how the parallelism achieved in Kafka. Partitioning is super important, and also it's affects the ordering of events, because sometimes we use the keys, and then the keys define which partition the data will get into, and it affects the ordering. So partitioning is critical for Kafka. I would even say that partitioning somewhat more critical for Kafka, because if it's done not correctly, Kafka will make the life of the server's nightmare. So it's even more critical than what it is in Iceberg. And in Iceberg, partitioning is quite important, because if we partition data in a better way, then it would be easier to do pruning. So we can easily navigate to the chunk of the data which we need to process to respond to that query. So, and with pruning, it affects the query cost. So if we can partition data in a more sophisticated way, then we can limit which partitions we should touch and which should be discarded, and which files we should touch there. And we kind of limit the amount of data we should read for a query, which affects the cost. So, and that's kind of an interesting thing. So in a Kafka Connect, there is more like approach of fire and forget. So you just use it based on the time, and then there is not much of the concept of some smart partitioning. Apache Flink, you can handcraft that partitioning however you want, and you can also align the partitioning structure with the business logic that would still live in some queries in Apache Flink, and you will have to maintain those and adjust them as life changes. But it's very flexible and very powerful. At Constant Tableflow, we actually went more or less Kafka Connect way, and we decided not to overthink partitioning for at least right now. But what we do it, because partition, the danger of this approach of Kafka Connect and Constant Tableflow is that if we partition it by time, and there is a lot of data coming from the data streaming part, then it means that we will have a lot of files on the Iceberg side. So, then if we don't maintain those files, the queries will take longer to read, because we will have a lot of small files. And this is just the nature of the data streaming. And if the system is very intense, and usually like the systems which rely on Apache Kafka, they have tons of events happening. So it ends up in a lot of small files. So how we decided to approach this is that we still do the time ordering. So we don't do anything sophisticated for partitioning, but we do the maintenance of those files. And we actually then process them, and we, from the small files, we create a normal snapshots with the bigger files, which is easier to read, and then it is easier to work with, and that's how the performance is improved. The next challenge for the bringing the data, or the next concept, which is quite important, is like guaranteeing that the data which is processed from data streaming into Iceberg is kind of like it has some guarantees of being same, even if we have to reprocess the data again and again, so that we always end up with the same picture in Iceberg when we get the data from Kafka, if that's necessary for our product. Products are different, business requirements are different, but if it's necessary, and if our goal is correctness, we don't want to have any deviation and any kind of changes, then we need to apply exactly one semantics. And how this can be done behind the scenes. For example, when we bring the data from Apache Kafka, we actually can do at least once processing. So we don't really need there this kind of exactly once processing. So we can do that at least one processing. But then when we go from job to the table, Iceberg table, then we do it in idempotent approach, so that we make sure that it's only once we store that record. And we use atomic commits for committing those changes, so that we either commit it as a solid block, or we discard if something just doesn't work or there are conflicts. And again, Apache Flink has checkpointing, two-phase commit syncs, transactional Iceberg sync. So Apache Flink, kind of the king here. It would not really like have instructions on how to do it, but you can do it with using those primitives. So Kafka Connect, and this is I might actually go and adjust it because I was looking into this. So I put the default as at least once, but maybe exactly once is also. Actually, we had like.
Yeah.
I
I was trying to recall this, but I wasn't entirely sure right now.
Yeah, I also need to double check.
Yeah.
So.
I'm not sure.
Yeah. So if the at least once is enough, then also it simplifies things, and then you have a bit of a kind of a grace for a failure. And not all products need exactly once, but that would I would be a bit careful with Kafka Connect, because here and how the logic is set there. So how we did it, we just look at the offsets, and we never commit the future offset if there is gaps in the. So offset is a concept of Kafka. It's like a kind of, you can think of the number of the record. So if I have the number of the records from 0 to 100 arrived, and then I have the records from 150 to 200, but this kind of a middle gap is missing, we are going to wait for those records till they arrive, so that we always have this consecutive flow of the data, and we just look at the offsets. And we also do the error handling there as well. So it's kind of aligned on the upper level. So it's kind of we suggest the default way how it works, and then all the tables follow that. Then another important consideration to make when you are moving the real-time data into Iceberg is how exactly you are going to deal with those late arrivals. So if you think of it, some data, and this is the nature of data streaming, some data might arrive later, and it may be some, of course, latency, some milliseconds later, but it can be also some minutes or even hours. So depending on, again, where the data is coming from, there can be delays. And then it can be mildly late, but then it would mean that if you, for example, have the window of that data processing, let's say we have a dashboard and we want to visualize all the latest information in the dashboard, and we do it like per day. But then the data arrives like I don't know, a bit later after the midnight. Then the dashboard will miss that information if we decide to cut it per day. If we decide not to cut it at all, then we might end up that we are rewriting always that history. And then if you look at the dashboard an hour later, even for yesterday, it would have a different information because late arrivals came. And also the danger here, if you're using the keys and the ordering of events is important, then we might get also data out of the order, whereas then the kind of the sequence of the changes would ruin the whole flow. And then depending on the arrival order, we will have a different picture in Iceberg table with a different sequence of those events. So we need to be careful and also to treat those later arrivals. And there are two strategies. On one side, we can indeed, like say we are cutting off, we have this per window. So let's say one day, if the data arrives after a certain time later, we just ignore it. It's kind of easier to work with. Also, it makes it easier to maintain those snapshots. So it's kind of, we know that the door closed. We just don't take any later hours. However, for many industries, losing that data, like which arrives a bit later, is not acceptable. And if you work in the industries which are more strict, which not allow like financial, health industry, whatever we have, that's not an option. So we have another approach is that we always merge. So we need to ensure that we have the final correct logical state of the data. So whenever the data comes later, we still need to integrate it into our tables. So, and then you can also travel in time through those states, and you will see those like extra new changes added. This is more complicated, but always merge is probably preferred by majority of the industries. So Kafka Connect doesn't have that concept. So that's where you just process it as like flushes the data as it is, and then you will have probably to take care of that on your own. Apache Flink is always the most flexible, the most powerful, comes with responsibility to encode that policy. And in console and table flow, as I was mentioning before, because we are waiting always for those offsets, we are not missing any information. So the order always is correct. And we do update the late information. So we go with that always merge approach. And the final important part is maintaining that data in Iceberg when it comes from Apache Kafka. And the problem with that is that because, again, the streaming data produces so much data, we create a lot of small files. And on top of it, we have metadata, all data, and this will slow down the system if we don't really go and then do certain cleanup operations. And this is something which is difficult to prevent because it's just the nature of how Kafka works and how like it's a different realm from Iceberg. So that's why we need to do the compaction. We need to think about retention of snapshots, so like how long we keep the data, how far into the past we need to look at, and then time to leave policies for any deletes which are more granular, and in general clean up all whatever mess is there. So there are not really built-in tools for Kafka Connect. However, both for Kafka Connect and Apache Flink, there are a number of options which you can employ, just external options which you will have to do. We also do it at Confluent Tableflow. We do the compaction, the maintenance. This is kind of we align job and compacting and cleaning up all together. Other options, and this is not, I need to update at least. I'm sorry. But the other options, there are a number of different approaches how it can be done with Spark, Trino of Flink. So the issue of compacting, of course, is real, and we have to find and deal with it. So and yeah, so this is my final slide with all the nodes plus operational complexity. But the point which I wanted to make is that when we deal with this transition of the streaming data into Iceberg, it's not only just stream, like convert and forget. There is operational complexity of maintaining all of that, making sure that again, we can still efficiently query that streaming data. And yeah, so, and then you will have to make a choice how exactly you're going to do it and which tools you're going to use, depending on the use case and depending on the constraints of the project which you have. So going from like maximum flexibility to maybe less flexibility but more simplicity, or to some predefined options. And that's it from me. Thank you so much.
Thank you, Elena. So now you have a possibility to ask about Kafka, I guess. Oh, no.
So one quick question in your slide about exactly one semantics. If I recall correctly, you started from Kafka, but if you want to have end-to-end, exactly once.
You mean from Kafka to Iceberg,
Well,
or?
something got the events into Kafka, right?
Yes.
So if you want to guarantee exactly one semantics, it needs to be end-to-end, because if that's something else, that's including events, is duplicating or losing stuff, then
yes.
Purpose,
No, definitely. And in some scenarios, like let's say financial transactions, you must have end-to-end. And we do have transactions. So we do have transactions in Apache Kafka. We do have mechanisms how we work with the exactly one semantics. I think it's more or less that there is this gap between Kafka and Iceberg. So this is where I focus. But we do have tools for that as well.
You recommend using?
Exactly one semantics in Kafka. I do recommend when they are necessary, because it's all the compromise. So Kafka in generally, it's the system which built like for speed. And then the less constraints you put on the data, the faster the data will move. However, often we need the guarantees of the ordering of the events. Often we need to make sure that it's processed exactly once, and then we have to put extra constraints. Sometimes you need like at least once is enough. That will be already faster. So the more like you really, it's like the minimum necessary requirements. That's what I would suggest.
Can I ask another question? So what are your thoughts on dumping that into Iceberg through tiered storage? Because you talked about reading from Kafka and landing it on an Iceberg table. What about landing it through tiered storage?
Tiered storage, for example, in which context, in which technology?
You're sending code segments to it.
So the thing is, I think that depending also like what technology you're already using. So, and I think that so far we have seen that like there is such a zoo of different technologies here. Dumping it there from tiered storage is actually a pretty valid approach if you already bring it to tiered storage. So this how it works with Confluent, for example. We read some data from the brokers, but generally it's not like we actually already dumped that into some shape or form of tiered storage, and from there we bring it to Iceberg, so that we don't overload brokers by reading the data directly from the brokers. So I think it's totally valid approach. You will have also to solve a number of issues there when you are moving, because again, so in tiered storage, in which format your data is. So that would be my question, because if like, I guess it will still not be Iceberg friendly format, unless you're, but then you're moving the Iceberg, like at some point of time, you will have to convert it to Iceberg files. And the question is at which point of time it will be, before tiered storage or after?
So tiered storage is a Kafka feature, right? You can move segments into tiered storage, to code storage, if you want to call it like that. The question is, right now it's not so you don't have to store in an open format. So my question is, because there has been a lot of discussions about this, right? So whether that format should be an open format, like directly linking data in Iceberg format. And there are lots of, I don't know, I've seen a lot of concerns about this. So I was just wondering about your thoughts on that.
No, I think I also don't sometimes like to. So I think there is a lot of also conversation how we should align, and if we should smarter like restructure stuff, or like Iceberg. we lose sometimes flexibility. We impose format tiered storage should have the data for convenience for this use case, and sometimes we lose the whole picture. So I have only opinions, I would say.
You gotta take the consultant answer. It depends.
It depends. So yes.
Thank you. Perfect. Any other questions? Not the case. Elena, thank you very much.
Oh yeah.
All right, guys, you made it. 3 hours hardcore Iceberg. Thank you very much. It's not easy sometimes to listen 3 hours Iceberg, but it looks it's worth it. And again, thank you, Cantox, thank you, ClickHouse, and thank you for everyone who was listening. And hopefully next time you're gonna be here on the stage presenting your experience of using Apache Iceberg. Thank you.
So is that a promise that there'll be a next time?
Well,
Why not?
oh, look, it depends if you're gonna be on stage. Okay, guys, thank you. So we still have 5 minutes just to have a conversation, I guess. And there's some dessert remaining on a table, so grab it, talk, and let's connect and talk about Iceberg. Thank you very much. Bye-bye.